Good evening, everyone. So, this is our 10th session. So, we will be having two more sessions, and I think today we will be discussing two questions as usual. Uh, One would be based on liquid propellant pumps, and another would be monopropellant rockets, or designing the combustion chamber for monopropellant rockets. Okay. If you have any doubts in between while I'm solving, please feel free to stop me. And if you have any doubts from the assignments or anything else, we will discuss that at the end of these two, after solving these two questions. Okay. I believe I'm audible to everyone. Um, am I audible to everyone? Can anyone please confirm it?
Yeah, we can hear you.
Yes,
Okay.
sure.
Okay, thank you. Thank you. All right. Today the first question will be based on liquid propellant rockets. Specifically, it's liquid pumps, uh, which pressurizes the liquid propellants and injects. So basically, we are trying to see the performance of the pumps using this. Okay. So um, let's read out the question. Let's understand what the question is asking. Okay, the pump is operating at a speed of 18,000 rpm. So there is a pump which is operating at a speed of 18,000 rpm, and it is feeding liquid propellant. Okay, and the liquid propellant's density is given, um, and it also provides at a mass flow rate of 72 kg per second into the thrust chamber. So the pressure rise across the pump is 5 megapascal. So the difference between pressure from the inlet of the pump to the exit of the pump is 5 megapascal. Okay. So a request is received to upgrade the performance of liquid rocket by increasing the pressure rise across the pump to 7.5 megapascal. So right now they are using 5 megapascal pressure rise. So in order to improve the performance of liquid rocket, our rocket engine, they are trying to increase the pressure ratio. So they want chamber pressure to be high as 7.5 megapascal. If we need chamber pressure to be high as 7.5 megapascal, we need to pump our liquid propellant to 7.5 megapascal. So um, so that so for that, what changes we need to make in pump is what this question is about. Okay, while so we are planning to increase the pressure to 7.5 megapascal while retaining the same diameter of the impeller, which means I'm not going to change the pump or the impeller, um, but I want to have a pressure rise of 7.5 megapascal. So if I want to do that, what I need to do, right? So based on basic understanding, you could say that I need to increase the rpm of the pump, right? So we'll see how it is happening. Okay, so we were asked to find so we have three questions to answer. One is volume flow rate of the upgraded pump. So when you increase the pressure across the pump, what happens to the volume flow rate or the mass flow rate? Is it remaining same? What is the upgraded version of it? And the specific speed of the pump, for which we know the formula, we just need to find it, and the rotational speed of the upgraded pump. So what should be the my rpm if I want to have a 7.5 megapascal pressure rise? Okay, so this is what this question says. So let's quickly write the given data, and here we have a definition for specific speed and specific diameter, and you all know how it comes. It comes from Buckingham White theorem, right? So from there we derive it, and we get the specific speed and specific diameter relations. All right. So let's quickly write it down. So there is this pump already. Um, so let's call it pump one. Okay, and the pressure rise is 5 megapascal, and the rpm is 18,000 rpm. Okay, and the propellant density. The propellant density is not going to change, so it is going to be same even if you upgrade it. And the mass flow rate, so mass flow rate is going to be 72 kg per second. Okay. What else is there? That's it. So we want to upgrade this pump. Okay, we have this pump, we need to upgrade it to a higher version of this pump, let's say pump 2. Okay, but the diameter is going to remain same, or the pump is going to remain same, but we need a pressure rise of 7.5 megapascal. Uh, what has been asked is volume flow rate of this pump. What is this? Okay, and then uh, rotational speed of the upgraded pump. What is n of this upgraded pump? So to avoid confusion, we will put 1 here, and we will put 2 here. Okay, and given this question, um, how do you solve this problem? So let's say first I want to find out volume flow rate of the this upgraded pump. How do you find out? Do anyone have any idea?
So first we
So
find the
I
specific.
Yes, Anirudh, go ahead. Specific.
So first we find the specific speed with all
Okay.
those values, and then we try to finding out the flow rate.
Okay, so we use specific speed to find. First, we will find specific speed, and then we will. So you are telling specific speed is going to be same for pump one and pump two.
Yes,
You will
sir.
be able to get right.
Yes, sir.
Okay, so basically, this is a design characteristics of a pump, right? So once it is designed, you are not changing it. So this, what do you say, the specific speed and specific diameter is not going to change for a pump. Okay, so if you just want to change the operating conditions, you should have same characteristics of the pump. Here it is, specific speed will remain constant, that is true. uh, okay, so from here we can try. So let's say if we just write the equation for this. So it's going to be omega 1 square root of q dot 1 divided by delta p1 divided by rho whole power 3 by 4 is equal to omega 2 square root of q dot 2 divided by delta p2 by rho whole power 3 by 4. Now how do you uh, calculate? How do you do? So see, do I know everything in this formula? See, I can
I
find
guess
omega.
we don't know the omega 2. I guess we don't know the
Yeah,
omega 2.
we don't know omega 2, we also don't know q2. We can't find using this formula, right?
Yes, sir.
Okay. So, how do we go about? Sri Lakshmi, you want to add? I think you also try to answer.
yeah, what I was thinking was maybe Q1 is equal to Q2.
q1 is equal to q2. Why do you say that?
Um, Honestly, I'm just guessing actually.
Okay. So, see, for a given pressure ratio, you cannot have same Q1 and Q2. Okay. So let's say you are changing the pressure ratio. When you change the pressure, what happens when there is a pressure gradient? Your velocity is going to change, right? So when for a given area. So if you think in that perspective, if you don't go into turbo machinery concepts, if you just think into that perspective, when there is an increase in pressure, you cannot assume that uh, the flow rate is constant.
No, okay, okay. Yeah, that makes sense.
So ideally, if you uh, see, you are thinking, yeah, I understand from where this is coming. Like you are just applying continuity, right? A1 V1 equal to A2 V2, right? So that's when Q flow rates will be equal. But that is in the same scenario. If you see um, uh, flow rate in a varying pipe, or let's say in a nozzle, right? Where rho A1 equal to rho A2 V2, or rho AV at throat is equal to rho AV at exit. So those things happens within the system. Here you are changing totally the operating conditions. So when you change the operating conditions, you cannot assume that these two flow rates will be same. So you should think what is given, what is the distinguishing characteristics between what is something like common between pump 1 and pump 2. What did we say in the equation? We want to increase the pressure across the pump, we need to increase the pressure rise across the pump, right, while retaining the diameter of the impeller to be constant. We don't want the diameter to change, right?
So I guess we can use that ND equal to DI rho P upon rho,
Exactly.
that
So,
equation.
because here we know that for pump we are not changing pumps, so ND is going to be constant between. I mean, for both the pumps, ND is going to be same. And now we also imposed another condition telling that DI is same. So in that case, we can let's try it. So you will be clear. So N D1 is equal to N D2. So basically, if you write it, ns1 is equal to ns2, because we are just changing the operating conditions. So these two parameters needs to be same. Okay, that is true. But in addition, what we said was, we said d1 is equal to d2. Okay, we are not changing the impeller diameter. So then what you should do is you should use these two relations in order to find the flow rate. So that would be clear if you just substitute it here. So what is ND1? It's going to be D1 times delta, isn't it? Delta P by rho power 1 by 4 divided by, I think it's square root of Q dot. So here make sure it is 1. And similarly, sorry, this must be 2. Diameter of 2, delta P2 by rho 4 power 1 by 4 divided by square root of Q dot 2. So now, since we know D1 is equal to D2, these two is, it goes away, right? Similarly, we also know rho is not going to be changed. I mean, the working fluid is still the same. We are not changing the propellant. Now, if you rearrange this, what happens? Delta P1 power 1 by 4 divided by square root of Q dot 1 is equal to delta P2 power 1 by 4 divided by square root of Q dot 2. So here what we know delta P1, we know the desired condition what we need to reach, and we also know Q1 dot. Now you can easily find Q2 dot, right? So let's try to rearrange this. Whether if you have doubts, you can ask me. So if we try to rearrange this, what happens? Delta P2 by delta P1 1 by 4, right? So what we need is we need to find Q dot 2. What we could do is Q dot 2 by Q dot 1 is equal to delta P2 by delta P1 power 2 by 4, which is going to be 1 by 2, right? I'm just squaring both sides, and then so you can find Q dot 2 to be Q dot 1 times delta P2 by delta P1 whole power 1 by 2. So you can derive this formula and then calculate q dot 2, or if you want a simplified manner, you can just find nd1, right? First you can find what is the specific diameter, and then you can use the nd2 formula to calculate the q dot 2. That is also fine. So doing this will give you what is the dependence. So when we increase the pressure by twice, how are you changing the volume flow rate? How much rise in volume flow rate you will be seeing? It can be easily inferred from this equation. So let's substitute all the values we have. So what is q dot 1? Okay, we didn't calculate q dot 1. Did we calculate? No, m dot is given. How do we calculate q dot 1? What is q dot 1? Given is just mass flow rate and density. What is volume flow rate? Hello? Can anyone hear me? Hello? Am I audible? Okay, okay. Okay, so I thought I got disconnected. I thought there was a problem with my uh, okay, okay. So I thought there was problem in my side. That's why I stopped. Uh, so how do we calculate q dot? I think my screen just got struck. Okay, I think there is a problem with my screen. 1 second. Just give me a minute. John, John. Were you guys able to see my screen? Uh, I think I'm not getting. Anirudh, can anyone hear me? Okay, can anyone speak up? Mm, Hello, can anyone speak up?
Yeah, can you hear us, sir?
Yeah. Now I can hear you. Yeah, I think there was a problem with my speaker. I don't know what happened suddenly. Anyway, um and my screen also got stuck. I don't know. All right, no problem. Let me check my recording once. Okay, recording is keep going on. All right. So, so where did I stop? So where did I stop?
So flow rate.
Okay, so you guys understood. I mean, I was connected till I developed this relation, right? Q dot.
Yes, sir.
Okay, okay.
Yes.
All right. So how do we find Q dot one?
So dividing the mass flow rate by the density.
Right. So how much is that coming? I think it's 72 kg per second divided by density is 975. Right. How much is that?
So 0.0738.
Okay. So let's make it 0.074. Okay. Uh, meter cube per second. Right. So we have q dot 1, so we can go ahead and calculate q dot 2. So q dot 2 is going to be q dot 1, which is 0.074 times the pressure difference in our second pump or the upgraded pump is going to be 7.5 megapascal, and the pressure difference in the first pump is going to be 5 megapascal, right? So how much is the flow rate coming?
So 0.090.
Thank you. 0.090 meter cube per second. Okay. So yeah. So the first question is done. We found out what is the volume flow rate of the upgraded pump. Now we need to find specific speed, which is straightforward, right? You just need to directly substitute in the formula. It can be either pump 1 or pump 2, but we cannot do pump 2 because we don't know omega 2, right? Uh, we will find out sooner. So right now we will use the pump 1's data. Okay. So this is also equal to omega 2 square root of q dot 2 divided by delta p2 by rho power 3 by 4. Okay. So let's use this formula because we don't know omega 2. Okay. um, if we do that, what is omega 1? So we have some rpm given, 18,000 rpm, right? N1 is 18,000 rpm. 18,000 rpm means rotations per minute, right? uh, how do we convert it into uh, radians per minute? All right, this is again a problem, I guess. Hello. Hello. Yeah, thank you, Srilakshmi, but I think my iPad is creating some problems. Give me a minute. Let me restart it. Okay. Right. For some reason, I'm not able to see my own screen here. Were you guys able to see that? Is it? Okay. Why I'm not able to see, I don't know. Okay. I think there's a problem with my computer. Let me log out and come back. Okay. Yeah, you can stay because my iPad is connected, so you can stay. Let me log out from your computer.